So, hello. I greet you wherever you are. So, this is going to be our starting point in learning differential equations 2. So, in differential equations 2, what we'll be discussing a lot will be Laplace. Okay, Laplace transforms. So, in differential equations 1, we learned how to solve differential equations by using method of separation of variables and other methods that we were taught, the method of characteristics and what have you, method of undetermined coefficients and a whole lot. Okay, but those are not the only methods that you can use to solve differential equations. There are others. Okay, so sometimes we encounter certain problems, and when we encounter such problems, the methods that we know will feel as they can't solve some of them. So we use the Laplace transform to solve initial value problems with ordinary differential equations. Okay, so we are going to introduce that. So this is the first lesson. So the Laplace transform is most useful for solving linear, and I know you learned classifications of differential equations, so you understand what we mean by a differential equation being linear. So constant coefficients, that means that I have to have a variable coefficient. So the Laplace transform is most useful for solving linear, constant coefficient, ordinary differential equations when the inhomogeneous term or its derivative is discontinuous. I hope you know what the inhomogeneous term is, right? So when you have a differential equation, let's say y prime plus some ay prime plus by prime plus, maybe let's say cy equals f of t. This here becomes the inhomogeneous term. Okay, so if this is equal to 0, then our differential equation is homogeneous. If not, we have the non-homogeneous or inhomogeneous term. So when the non-homogeneous term or the inhomogeneous term or its derivative is discontinuous, we have an initial value problem when the differential equation is linear and we have constant coefficients, then we can employ the Laplace transform we learned in our math methods to find the solution of such a differential equation. So before you can really understand this course and find things easy, there are certain things that you have to know first. So the prerequisite is you have to know your forward and inverse Laplace. If your Laplace is very weak, you are going to have problems with this course. Okay, so in this first video, in the first 1 or 2 videos, we'll just take a quick recap of some of the things that you learned in Laplace transforms from your math methods course. So Laplace transforms. The Laplace transform of a function, say f of t, is denoted by what we have here, right? And it is defined by the integral transform this. I know this is not your first time of seeing this. So that is how we define the Laplace of a function. So take note of that. So let's go through the Laplace of certain functions. Okay. So we have a function here, f of t, and this here happens to be the Laplace of it. So when you have a, where a is any number, when you find the Laplace of that, it will be a over s. Okay, I know you might have known some of these, but let's just revise ourselves. So when you have of it, when you have 1, since the Laplace of a is over s, that means when you have 1, Laplace of 1 over s. If it is 3, it will be 3 over s. Then when you have the exponential function, e of et. All right, when you find the um, Laplace of it, it is 1 over s minus a. Some of these we will show them in the video as to how some of them is true. Okay, then when you have the exponential function being multiplied by any function f of t, so this is what you learned in your math methods course called the shift theorem. So we shift s by a, so we have something like this. Then when you have tn, right, the Laplace is given by n factorial over s exponent n plus 1. So when you have the exponential function attached to it, then you shift the s by a. Then when you have sine bt, this is the Laplace for it, cos bt, this is the Laplace for it. When you multiply by t, this is the Laplace for it, and this is the Laplace for it. Okay, so as the course progresses, you're going to learn of something called a Heaviside function and a Dirac delta function. So Heaviside function and a Dirac delta function. So we can also find the Laplace of those functions. So for instance, when you find the Laplace of this Heaviside function, you get this. So with this one, so you get this. Then this is the Dirac delta. So this two, you get that. Okay, so yeah, this was just to remind you of certain things you've learned before. But don't worry, this is your first time of learning it. You've seen something. Okay, so at the latter part of this video, I just want to show you how some of them was derived. We don't just write them, we derive them. Okay, and the derivation was made in your math method course. In your differential equation, you just have to know them and use them to solve your differential equations. And in case you want to know how some of them came by, let's solve this example to know. Okay, so we have to find the Laplace transform of the following. So a1, this, that, and that. So let's solve them. Okay, so we have to find the Laplace of a. So when we began this video, we defined the Laplace transform. So from the definition of the Laplace transform, the Laplace of any function f of t is given by what we have here. Okay, this is termed as the kernel. So we are finding the Laplace of a. It means our f of t is a. So wherever we find f of t, we replace it with a. And we are going to employ the use of improper integrals here. And that was something you learned in your math methods course. So that means the Laplace of a will be equal to integral from 0 to infinity this times a dt. So a is a constant, so we can bring a outside. So right now we are not doing differential equations, we are doing calculus. All right. So when you bring your a out, then that means you're going to have something like this. Okay, and you learned from your math methods course that when we are integrating and any of the limits of integration is infinity, we have to choose something which approaches that. So we choose m to approach infinity so that we can replace that with m and be able to solve that improper integral. Okay, all right. Then we also know how to integrate an exponential function. So when you have an exponential function and you have to integrate something like this, you maintain a function and you differentiate it with respect to the t here, and so the function here, you differentiate with respect to t, so you get a. So that means this will be this over a. So here too, we maintain what is here, and we differentiate it with respect to t, the function here. And that gives us minus x. So that way we have something here. Now the limit of integration is 0 to m. Okay, all right. So we can bring our s here so that we have e over s then times e minus st, then m to 0. So now we have to put in our limit of integration. So when you put in that, you're going to get this here, right? So now we have to evaluate it. So, when you put 0 here, in number exponent 0 is 1. So that means this is going to give us 1. And here, you just have to do a bit of analysis. So you can take e exponent any big number. So you realize that as a number is very big, maybe 1 million, because infinity is very huge. M approaches infinity. You realize that this thing here will be approaching 0. So that means this is going to be 0. So the Laplace of a is equal to a over x, then 0 minus minus 1. So when we evaluate what we have here, we are going to get 1. So a over s times 1, which will be a over x. So that means the Laplace of a is a over s. Right, so you can see that from the table here. You can see we've shown that. So we didn't just write them. All of them they were derived, okay? So let's go to the second one. So the second one says we should find the Laplace of 1. So this is an exercise to you. Just use the same concept we used in solving the first one to solve that, and you arrive at 1 over s. Just wherever you find a, you put 1 there, okay? So the third one says we should find the Laplace of the exponential function. So by comparing it with this, that's from the definition of the Laplace transform, that means f of t is this. So we just put that inside this here. We have this equation here. So the rest is our improper integral, our knowledge from math methods. So when you have an exponential function ex times ey, the same as ex plus y, right? So here, so that means since they are multiplying, we can add their powers, right? So when you add them, you're going to get a minus st. So that's why you have something here, like this here. Then we just want to put this inside this form. So you can see that when we've just manipulated this to get this. So when you should simplify this, you're going to get back this, okay? So dt. So yeah, we have to let our m approach the infinity so that we can go ahead with our integration. So when you are integrating exponential functions, like I said, we integrate the function, we differentiate the function here, and that becomes the denominator, and we maintain that particular function. So when you differentiate what is here, you're going to get you're going to get s minus a, negative of it, all right? Then times e minus s minus at. So we just maintain what was here. And the limit of integration is from 0 to m. So now we have to put in our limit for integration. So just from the same analysis we made when we were solving question 1, as m approaches infinity, this becomes 0. And here, when you multiply 0 to, you are going to get e raised to the power negative 0, which is 1. So you get 0 minus 1 here. This will give you negative 1. So when you multiply them, the negative 1 times negative 1 will give you positive. So we end up getting this. So that means the Laplace of EAT is this. So you could also see that one from the table here. This. I told you all of them, they were derived. We didn't just write them. Okay. Then I think let's solve the last one. So the Laplace of sine bt. So from the definition of Laplace transform, this holds, right? So you find the Laplace of sine bt. So that means our f of t becomes bt. So we put that inside this to get what we have here. So wherever you find f of t, we just put sine bt there. So now you have to do this integration. Someone will say, maybe let's use integration by parts or something like that, but that's going to be quite complicated. You work and work and work. So we want to change the sine bt into an exponential function so that we can easily use that one. And before we can do that, we have to go back to the discrete math we did, right? Or the complex analysis we are doing. Then we go to the Euler's formula, which shows us the relationship between the exponential function and cos and sine. Okay, so from the Euler's formula, then this holds. Okay, so you can see that sine theta is the imaginary part of this, because there's a real part. I hope you remember your complex numbers, right? And there's the imaginary part. So that means that sine theta is just the imaginary part of this. So we can say the Laplace of sine bt is the same as the Laplace of the imaginary part of eibt, because now theta is bt, right? So it is imaginary because of the I here. So that means the Laplace of sine bt will be equal to the imaginary of this integration. So e minus st dot eibt dt. So you could see now we've been able to change the sign into like an exponential function. So that will make our integration very, very simple. So as I told you, when you have this, it's the same as this. So that means we can add the powers. So when you add them, you are going to get this. Okay. Then we do our integration. Alright, so as time approaches infinity. Coming. So when you integrate what we have here, and I've told you how to integrate exponential functions. So you always, when you have something like this, when you're integrating this, let me even make this x. So when you're integrating this, you maintain the function, then you differentiate what is here. So what is plus c. Alright, so when you integrate this, you're going to end up with this. Okay, so you end up with this. Sorry, wherever I find my infinity, let me put my m here because m approaches infinity. So when you have something like this, then the next thing for you to do, just look at it, it's very simple, is to put in your limits of integration. Okay, so when you put in your limits of integration, you realize that as m approaches infinity, this thing here is going to be 0. So you're going to have 0 over s minus ib. And 0 over any number is 0. And when you multiply 0 by the power, you're going to get e minus 0. Like e raised to the power 0, which is 1. So you get 1 here over what we have here. So minus and minus will give us this, the positive of this. Okay, so that's how we end up with this. So don't forget what you are doing. We are trying to find the Laplace of sine bt, and that happens to be the imaginary of what we have here. So when you get something like this, the next thing for us to do is to conjugate it. So we are using our knowledge from complex numbers, right? So we have to multiply through by the conjugate of the denominator, which is s plus ib. So when we do that, 1 times s plus ib will give us s plus ib. Then s minus ib times s plus ib will give us s squared plus b squared. Okay, you can do that. So know that the Laplace of sine bt is equal to the imaginary of what we have here. So that means you have to separate this. Okay, so we can write this into the real part and into the imaginary part. So This is the real part, and this is the imaginary part from what we have here. Just like how when you have something like a plus b over c, you can write it as a over c plus b over c. That's the same concept we used here. So now you can see that the imaginary part is this. So the Laplace of sine bt is equal to b over what? S squared plus b squared. Finished. Right? So yeah, find the Laplace of cos bt. It's very simple. So that's going to be the real part of everything that we did, which is s over s squared plus b squared. Okay, so you can do that. So this was just a quick introduction or a quick review of a quick introduction about what you're going to do in differential equations too and what you have to know. So your Laplace has to be very, very strong. Okay, so you try to solve more questions on that. So the next video is going to capture inverse Laplace transform. So we've talked about the forward Laplace. In the next video, we talk about the inverse Laplace. Okay, so yeah, thank you very much.